Hi, I'm Anupama Mampage with the Clouds Lab at the University of Melbourne. Here I'll be presenting my research titled Deadline Aware Dynamic Resource Management in Serverless Computing Environments, which was conducted under the supervision of Professor Rajkumar Boya and Professor Shanika Karunasekara. First, I will briefly talk about the concept of serverless computing and then move on to explain what we have tried to achieve through this work. So as you all know, serverless computing is a service model in the cloud where the cloud provider allocates machine resources on demand to the user or the applications and take care of the servers on behalf of the customers. So developers get to focus fully on the application logic and not the infrastructure. So let's see why serverless computing has gained a lot of interest in the past few years. Among the many features of this computing model, the ability to scale resources up and down at a very fine granularity has a special place. Along with these features, serverless platforms usually have a very fine-grained billing model as well, such that the user is billed only for the resources consumed during function executions. Also, due to the automated nature of the server management process, these environments require very little user intervention for application deployment and execution, which results in lowered complexity for the developers. And also today, this concept is being explored for adoption in resource-constrained edge and fog computing environments as well. Similar to the benefits, serverless computing has some inherent challenges as well. The shift of the resource management responsibilities to the provider means that the platform has to undertake all these tasks, although it may not know all about the applications that are being deployed. And this being a multi-tenant environment makes it quite challenging and complex. Also, the setting up of resources required for function executions in the runtime, which is needed for auto-scaling feature, causes unfavorable delays to the user. And also another challenge is how to manage cache and application states where required. Since the serverless architecture has clearly separated data management from function executions, this has created limitations for certain data-driven applications. On the user side, although the serverless nature of shifting responsibility to the provider is a blessing, the lack of visibility to the resource management process makes it difficult for developers to assess the platform under different scenarios and also do budgeting and planning work. Also, the customized nature of the required function deployments has again created fears of vendor lock-in as well. So that's basically a very brief introduction to serverless computing. Now let us move on to details of our work. Our work focuses on efficient techniques for function scheduling and the management of allocated resources. So here we have presented some works in the literature related to those areas under serverless computing. We have identified each work in terms of the application model, the awareness on the deadline, efficient usage of online resources, and the dynamic nature of resource management. From this study, we could see that in summary that most of the existing works do not explore ways of achieving increased resource efficiency on the provider side using application-specific characteristics. And also fully dynamic resource allocation and scheduling has not been explored much. So these two will be the focus points of our work. Talking about the contribution from our work, we present a function placement algorithm which aims to have high resource efficiency. Also, we present a fine-grained approach to dynamically manage resource allocation, especially CPU resources to functions. And we implement our policies in a simulation environment and conduct a number of experiments. Also, we evaluate our policy against state-of-the-art algorithms and compare results. Moving on to the system model. So there's a set of events which trigger function invocation. And in our system model, we have a control element which acts as a gateway to the worker nodes underneath. It monitors the status of each worker node. So basically, it contains updated information on the functions scheduled on each node and the expected finish times. When function requests arrive at the controller, it undertakes load balancing based on this information that it keeps on monitoring. And we assume that the underlying VM resources are able to be switched on and off on demand. An active VM would contain multiple concurrent functions in execution inside a container at a given time. For a new request, a container with required runtime dependencies and the resource configurations will be launched. There's also a module called Dynamic Resource Manager in each worker node, which monitors the time to deadline for each application in execution. And it also handles dynamic container scaling and rescheduling as applications approach their deadlines, which we will be discussing more in detail later. Moving on to the problem scenario. So as we discussed before, usually under the serverless computing model, the user is not required to provide detailed information on their applications. For example, the resource requirements to the provider when deploying them. So the provider has to work with what is provided when doing all the resource allocation and scheduling and everything. In these environments, it's a common occurrence that certain resources, especially compute resources such as CPU, could get constrained in nodes in the runtime. This could occur due to several reasons. One could be that the resource demands being different from the initial resource allocation, and also due to system performance variations over time. So as a result, the static resource allocation process may work poorly in such a scenario, especially when applications have their own key voice goals as well, like a deadline in our case. So, and also under this model, the user gets charged only for the resources consumed during function executions. Although under a practical scenario, say a commercial serverless provider would normally maintain its resources such as VM pools for longer durations. This naturally raises the need for mechanisms to be in place for the provider to attain high resource efficiency while scheduling functions. Moving on to a more formal definition of the problem. In this work, we consider a scenario where function invocation requests arrive at a serverless platform with certain attributes. They have a specific function to be invoked, a priority level, arrival time, a deadline, and a memory request. Also, the platform has a set of compute nodes or VMs. Each VM has some available resource capacity defined by a two-dimensional vector, CPU and memory. And for the scope of this work, we consider an application to be composed of a single function. And the first objective of our work is to schedule functions on VMs so as to achieve a high resource efficiency to the provider. So the metric we measure is the total VM time during the experiment. We want to minimize the total VM uptime. And the second objective is to manage allocated CPU resources to functions so as to maintain application performance and meet the deadline. So the objective is to minimize deadline violations. Both of these objectives are subject to the resource constraints as shown in the slide. Moving on to the proposed solution. To realize these objectives, we propose a heuristic algorithm for the efficient placement of functions and a dynamic resource alteration algorithm. First, I will talk about the function placement algorithm. The proposed heuristic placement algorithm follows a deadline-sensitive function aggregation policy. So what we do is we try to aim to align the runtimes of function executions that is happening in a particular VM so that the underutilization of VM resources is minimized. That is, any VM would experience high utilization during its active lifetime. So an incoming request has certain parameters as we discussed before. Also, the dynamic resource manager module maintains a list of active VMs and their remaining expected runtimes. Now, in order to choose a node, we iterate over the active VM list. And if the request is for rescheduling, we avoid directing the request to its previous VM itself. Also, apart from the availability of sufficient free resources, a VM is considered for function placement only if its CPU utilization is below a defined utilization threshold. We do this because we do not want to overload certain worker nodes. So if these requirements are met, then a VM is chosen for execution of that particular function if the expected remaining time of the VM is greater than the time to deadline for the request, and the request bears a low level of priority. In case if it's a high priority request, we choose the VM with the highest free CPU resources out of the VMs matching the above criteria. If none of the active VMs with sufficient free resources have the required remaining active time, we choose the VM with the highest remaining active time. And if none of the active VMs have sufficient free capacity for the function execution, a new free VM is added to the pool. So that is the function placement algorithm. Moving on to the dynamic resource alteration algorithm. This aims to alter resource allocations to function instances approaching the deadline during the runtime. For this, the DRM, that is Dynamic Resource Management module, also maintains a list of functions in execution in each VM sorted by their remaining slack to deadline, which is also used in this algorithm. This algorithm is executed by the VMs each time a task reaches a certain percentage of the task's time to deadline from arrival. At this point, if the function is still in execution, the initially allocated upper limit of CPU processing power to the container is incremented, provided that the underlying VM CPU utilization is below the threshold, and also the container has not reached its maximum CPU allocation. Here we use the concept of CPU quota and CPU period enabled in Linux kernel's completely fair scheduler. And after each resource update, the VM is checked for resource overloading. In the presence of resource overloading, the algorithm proceeds to efficiently evict some of the most recently scheduled tasks, and this is done based on a rescheduling cost. This cost is determined by the time spent from request arrival and also by the time to reschedule. So once a task is chosen for eviction, its running container is destroyed. It frees up some resources for the constraint node, and the rescheduling of this task follows the function placement algorithm we discussed earlier. Moving on to the performance evaluation. So to evaluate the performance of our algorithm, we simulate a serverless computing environment using Container Cloud Sim simulator. We have set up a serverless environment with a cluster of VMs, each with 4 vCPU cores and 3 GB of memory. We compare our function placement policy with the baseline scheduling policies of round-robin random placement and bin packing heuristic. Also, we used fixed resource allocation and a CPU shares policy to compare against our dynamic resource alteration policy. We employ a number of synthetic and real-world traces to evaluate the performance of our policies. We use a number of synthetic workloads with varying incoming request levels to see how the system performs with the load. Also, we use trace snippets from Wikipedia and certain parameters from Azure function traces and build up a real-world trace to do evaluation as well. The performance evaluation of the function placement algorithm. In all these experiments, we observe 2 metrics. One is the total VM uptime during simulation time, and also the percentage of requests meeting the deadline. So these figures present results of resource efficiency. The study done using synthetic workloads. We compare the VM uptimes using our policy, that is DBP, with the baseline schedulers under different scenarios with dynamic provisioning of CPU resources and rescheduling as well. So the two figures depict results under different load levels when the incoming requests. One is when incoming requests have tighter deadlines, and one is when incoming requests have more relaxed deadlines. The results show that our method is able to achieve a high resource efficiency similar to bin packing heuristic, while the round robin and random placement schedulers show significantly higher resource usage levels, that is low efficiency. We also do experiments varying the time points of CPU provisioning as well. So these figures show results measuring the deadline satisfaction matrix. It is evident that round robin and random placement algorithms are able to show high levels of meeting deadlines here. So why this is? This is because they have a better opportunity of dynamically provisioning CPU resources to functions as functions approach their deadlines, since the initial function placement tends to happen in VMs with more free resources. So that's the reason. But even in that case, our method, that is the deadline-based placement algorithm, is also able to maintain a low level of deadline violations compared to simple packing heuristic, and while also reducing the provider cost by having high resource efficiency, as we discussed in the previous section. This fact is also clear from experimental results from real-world traces shown here. So using our policy, we could improve VM uptimes up to 3 times compared to round robin and random placement. Also, there's a good performance with regard to deadline satisfaction compared to a simple packing heuristic. This shows the performance of our load balancing approach of deadline-based placement with dynamic resource alteration compared with the fixed CPU allocation policy and a proportional CPU shares policy. It is seen that the suboptimal initial resource allocations and CPU performance variations over time could result in higher deadline violations under the fixed CPU allocation method. And under the CPU shares policy, since there's no guaranteed CPU time allocated to an application, performance of applications vary with the co-located applications, and this results in relatively poor performance as well. In comparison, our policy of SLA-aware dynamic handling of CPU time to each function is able to result in better performance under all the load levels, as you can see in the figure. In conclusion, having a fine-grained and a dynamic method to manage allocated resources to functions would definitely be suitable for an environment like a serverless environment. Also, definitely focus has to be given to having high resource efficiency on the provider side, given the fine granularity and billing and so on under these computing models. Also, considering the above 2 points, our proposed policies could show improved results. For future work, we would like to extend our dynamic resource management policy to incorporate more precise resource usage predictions using more dynamic monitoring techniques and profiling workloads and so on. We also would like to explore the resource efficiency paradigm more under diverse environmental conditions. We would also like to look into data dependency challenges for DAC-based application scheduling under serverless computing. Also, we would like to demonstrate the practical applicability of our proposed policies using an open source serverless framework. Thank you.